Let's talk about the basics of frequency and how musical instruments all fit together frequency-wise. This will help you to understand arrangement, production, recording, and EQ. I'm Keith. Let's get started. Now, we generally think of pitch in terms of notes. But there's another way to think of pitch, and that's in terms of frequency. On this graph in front of you, you can see the sound represented on the left, the low side, from about 20 Hertz to up above 20,000 Hertz or 20 kilohertz. That's the useful range for audio. The A below middle C we think of as an A, but it vibrates here at this main frequency of 440 Hertz. So when you hear the term cycles per second or Hertz, it literally means how many times that thing is vibrating per second, whether it be your vocal cords or a piano string or a violin string. And those frequencies can be translated to notes. Let's hear a sine wave of pure sound here at 440 Hertz. Now you can see that sound has energy here at 440 and not much energy anywhere else on the spectrum. It's just a pure sine wave. Here's a piano playing that same note, A440. Notice the fundamental frequency of 440, but also notice the other frequencies that are ringing. Yes, 440 rings. So does 220, which is mathematically related. 660, which is also a multiple of 220. 880, which is twice 440, and so on. All mathematically related, what we call harmonics, if they're above, and subharmonics below. And they define the tone of the piano. Here it is again. One of the things that makes an instrument sound different is the ratio of the harmonics to the fundamental. Now, why does the piano vibrate in all these different areas? Well, the piano string, the actual wire that's in the piano, not only vibrates as a whole string, but it vibrates in half, and it vibrates in thirds and in fourths. And so even though the main vibration is 440 times per second, there's all these sub-vibrations going on, and they create the harmonics. And this is why music doesn't sound like a sine wave. A440, an octave higher is 880, an octave higher than that is 1760, and so on. Here's my voice now, and you can see it has some energy down here around 100 Hertz, and the of the voice is strong here, and without that you wouldn't have the clarity of the voice. And the sibilants, the S's, the T's, and the ch sounds, are up in this high range. So the voice requires all of these components. Down here it sounds warm, here there's clarity, here is articulation. All these things work together, all these frequencies work together to make the sound of the voice. Now here's a kick drum, and look at where the energy is focused. So the main energy of the kick drum is right here, maybe around 60, 70, 80 Hertz, in between 50 and 100 Hertz. Now for a bass guitar. Notice that the main energy of the bass guitar is up a little higher than the kick. It's between 1 and 200 Hertz. So we have the kick drum down here, the bass down here. Where does the guitar come in? You'll notice the guitar takes up where the bass leaves off. Its main energy starts at around 200 and goes all through the mid-range. Cymbals, the high end of a snare drum, the S's and T's and ch sounds that we discussed earlier, they all live up in this range, and all together they make a blend of frequencies all throughout the audible spectrum. Now, this is true of most any form of music. For instance, a string section will have a cello, a viola, a violin. right? Each one of those instruments has its strong frequency range, and they all fit together. Of course, there's some overlap. Okay, that's the basics of frequency and pitch and how and why music all fits together. If you found this useful, hit like and subscribe. We'll see you next time. Bye-bye.